Let's begin with the synthesis of cholesterol. First, we start with our 3-hydroxy 3-methylglutarol coenzyme A, which is formed when acetyl coenzyme A condenses with acetyl coenzyme A to form our HMG coenzyme A, and that's done with the enzyme HMG coenzyme synthase. So our next step is to form mevalonate from our we'll just call it HMG coenzyme A, and we use the enzyme HMG coenzyme A reductase. And this is our rate limiting step, meaning it's our slowest step. So if we speed this one up, it's going to speed up the reaction a lot. If we slow it down, it's going to slow down the reaction a lot. And once we have our mevalonate, we use ATP forming ADP, and we get our 5-phosphomevalonate. So we're phosphorylating it. And then we phosphorylate it again using ATP and ADP, forming ADP, and we have our 5-pyrophosphomevalonate. And then we're going to use ATP again and lose the CO2, and we'll have our 3-isopentyl pyrophosphate, and then that will become our dimethylallyl pyrophosphate. And then using 3-isopentyl pyrophosphate, we're going to form our geranyl pyrophosphate, and using that same 3-isopentyl pyrophosphate that we used to catalyze this reaction is going to catalyze this one to form our farnesyl pyrophosphate. And this farnesyl pyrophosphate is going to form with each other. We're going to lose these phosphates by reducing them with NADPH, and that's going to form our squalene, which looks like this. So we have our squalene here. And then we're going to use our NADPH, oxygen, and an H+, and then these are going to form our, we're going to lose those as well and form our water as a byproduct in our NADP+, and then we'll have our squalene oxide. After that, we're going to protonate it and get protosterol cation, and then we're going to lose it, forming all these bonds and methyl groups, and that's going to be our lanosterol. And then, as you can see, we still have 19 more steps to form that cholesterol. Even though there are all of these other steps, if we go back to our beginning, we will have this step as our rate limiting step, meaning it takes the longest. Now, what we have is our lovastatin here, which goes into the stomach in its lactone inactive form right here, and then it is metabolized into its active form, the beta-hydroxy acid, in the stomach, and it functions to competitively inhibit the HMG coenzyme A reductase, which was our enzyme here that gave us our mevalonate. So basically we're inhibiting the synthesis of the mevalonate, which is then goes through all of these processes to make our cholesterol. And so it forms this active site, and it's a double whammy, so to speak, because it also helps lower cholesterol and its effects. So it also decreases the levels of high-sensitivity C-reactive protein. It improves the endothelial function, reduces inflammation at coronary plaque sites, inhibits platelet aggregation, and has anticoagulant effects. So, all of that, it decreases the effects that the cholesterol has, which we're most likely trying to lower the amount that's building up in our arteries to help lower blood pressure. But it also will stimulate the LDL receptors, the receptor expression that is, on the hepatocytes, which will further increase LDL catabolism. So we're getting rid of more of that bad cholesterol, that LDL. So it not only reduces how much is being made, it decreases the effects that what is made is having, and it also increases how much is getting catabolized. But that cholesterol is also used in good ways, like in our bile salts or in the formation of steroids. So that's why one of the effects of this is liver damage.